we're going to look at the extra stuff. For higher level. In the probability strand. So I mean, it's the probability and statistics strand, but the portion that's to do with probability. Since we've already done the ordinary level stuff on Thursday. So firstly, there's the addition rule. Okay. I'm just going to do a little note here. You know, we did the example of a class which had 32 people, and then in this class 26 people liked both ice cream and chocolate. One person liked ice cream but not chocolate. One person liked chocolate but not ice cream. So when we did the Venn diagram, and that's 4 people who, you know, are not included here. So of the 32 people, here's the 28 and there's 4 extra. So the reason I put that here is it's just handy to have an example when we talk about these things. So firstly, we look at the probability or the addition rule. So here, what we say is the probability that someone likes A or B. So then that means, you know, belongs to is one of these 28 people. Because so this circle is A, the set A, and that circle is, say, the set B. So if you want to know the probability that someone belongs to the set A, as it likes ice cream or likes chocolate, so then that means if you like chocolate but not ice cream, you know, you're included. Then that is just equal to the probability of A plus the probability of B minus the probability of A intersection B. So if you think about it, A intersection B is that you like chocolate and ice cream. So then you're one of these 26 people. And the reason you subtract that, so the reason you do minus P, the probability of A intersection B, is because if you just add A and B, you're overcounting. You're saying you're basically counting those 26 people twice. And to correct for that, you need to subtract once. So, you know, if I was just to ask you directly, what's the probability that someone belongs to either of these? Well, then you'd go the number who belong to A union B. You'd get 28 people, because it's 26, 7, 8, out of 32. But if so I'd remove that equal there. If I was just working that probability, I'd get 28 over 32. While if I do probability of A, well, that's going to be 27 over 32, because there's 27 people who like, say, chocolate. And probability B is going to be 27 over 32 as well. So that ends up being, you know, not equal to 28 over 32. But that's why we have minus probability A intersection B, and A intersection B is 26. So minus 26 over 32. So 27 over 32 minus 26 over 32 is 1 over 32. add that to 27 over 32 and you get 28 over 32. So then, the things add up. A variant of that, and we mentioned this part already, what is the multiplication rule. And I'd say add independent. So if A and B are independent, so if I toss 2 coins, or if I roll many dice, it doesn't matter what's happened before. They're all independent. Then probability that it's both A and B is equal to one bracket too many there. Probability of A multiplied by the probability of B. The new content, which we didn't do at ordinary level, is multiplication rule general case. So the general case means it doesn't have to be independent. So here it is the probability of both A and B is equal to the probability of A multiplied by conditional probability multiplied by the probability of B given A. So now this is the general case, so let's apply it to this example. So if I want to know what's the probability that somebody likes chocolate and likes ice cream, well, if I do it the direct way, I just count the number of people who like both. So that's going to be 26 people out of 32. Using the number probability of A is the number of events of type A divided by the total number of events. But if I want to use it if I want to try and get this using our new rule, well, it says probability of A multiplied by the probability of B given A. So the new thing here is, what does that mean? What is the probability of B given A? Well, the probability of A is, well, there's 27 people who like chocolate, or with A, ice cream. Right? So I know that's 27 over 32. The probability of B given A means the probability, how many people are of type B given they come from the set A. So B given A is going to be, I just look at the people who belong to the set A. So there are 26 people in the set A who like chocolate out of 27. And now if I multiply these, well, 27, or the two 27s cancel, and I get the same answer. So we can see that in this case, the multiplication rule works, or we can see how it works. And a little, the final thing to say on this topic is, remember, or it's important to know that, and because you might be asked, the probability of A given B does not equal the probability of B given A in general. So there could be examples where the two are equal, but in general they're not. So what I mean by that is, you're not able to switch. So you don't, if you have an expression where you have the probability of B given A, you can't in the next line just change that into probability of A given B. They're not interchangeable. And you can, in this example, they are the same, because probability of A given B is I have 26 over 27, and the probability of B given, or probability of A given B, is also 26 over 27. But you can imagine if, say, I'd said there are 25 people who like both, and 2 people like chocolate, and so then you wouldn't have the 2 being equal. So that's all we needed to, all we wanted to talk about here. We'd kind of touched on we'd mentioned the multiplication rule when you're looking at independent things already. So this is the new thing, to take away A intersection B because of the overcounting. So if you have an example in mind, you can kind of see what's going on and go, oh yeah, of course you'd have to take that away, because if I just add A and B, I get 27 over 32 plus 27 over 32, which is actually greater than 1. So that can't be right. You kind of probability is between 0 and 1, or 0 up to 1. So that's our first topic. So actually the next 2 topics are basically the same. I mean, like they naturally flow into each other. So binomial coefficients are just looking at, say you had, or a plus x to the power of n. Essentially, that actually follows a pattern. So the general rule is you have a to the n plus n choose 1 a to the n minus 1 x plus dot 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 plus x to the power of n. So you have n choose 1 a to the n minus 1 x plus, as well, do one more example so you can kind of see the pattern, a to the n minus 2 x squared plus dot 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 plus. So each time you go n choose 1, n choose 2, n choose 3 as the coefficient, you have a to the n minus 1. You're lowering the power of a and increasing the power of x. So that's a faster way of, you can work out 1 plus x squared, or you can work out 1 plus x cubed. It's slightly messy, but you can do that. But as the powers get higher, you're more likely to make mistakes, and it's kind of dull as well. So using n choose r, you can speed up and save yourself time. So the next thing is basically using this. You kind of go, well, why would I want to do this? Well, Bernoulli trials. So say you want the probability of k successes from n repeated trials. So if you tossed a coin 10 times, what's the probability that you toss 4 heads? That kind of problem. So the way you frame that is you just look at p plus q to the power of n. So p is the probability that you toss a head, and Q you toss tails. So this is not a fair normal coin. So P plus Q have to sum up to 1 because you're talking about a probability. So 1 to the power of n is equal to 1 as well. So now using our new knowledge of binomial coefficients, I can just expand what this is. I can say that's equal to p to the n plus p to the n minus 1 q. Do I have enough? N choose 1 plus n choose 2 p to the n minus 2 q squared plus, since p to the n minus 3 q cubed plus dot 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 plus q to the power of n. And in order to answer this question, what's the probability of getting k successes, I only need to look at the q to the power of n term. So probability of k successes is equal to, well, n choose k, p to the power of k, q to the power of n minus k, which is a pretty handy result. If you think of tossing 5 coins, I can get one head one way, I can get 2 heads 5 ways. One way, 5 ways. I can get 3 heads 10 ways. I can get 4 heads 5 ways, or 1 head, 2 head, 3 head, 4 head, and 5 heads one way. Because 5 choose 1, 5 choose 0 is 1, 5 choose 1 is 5, 5 choose 2 is 10, 5 choose 3 is 5, or 5 choose 4 is 5, 5 choose 5 is 1. So I get this shape of the highest point is in the middle, and then it's symmetric. This, as you increase it, so this is for if I have 5 different values I can get. So if I toss the coin 5 times, I only get these 5 values. But if I toss it, say, 1,000 times, and I look at it from afar, you get the normal distribution, a discrete version of the normal distribution. So there's also a natural continuity from looking at binomial coefficients and n choose r to looking at the normal distribution, which is the last thing we need to do. So all we really need to do here is look up the table book, and the best way, or the most natural way I could think of, is just to look at the exam question from 2 years ago, because basically it's the same type of question all the time. So here it is. You just have these components. So the diameter is 20 millimeters, and the tolerance is 0.25 millimeters. So what that means is, if the component is more than 20.25 millimeters in size, then the machine will break, or it won't work. It's not good enough. Also, if it's less than 19.75, because so the piece could either be too big or too small. Now, the producer or manufacturer well, they make components which are on average, so scratch that, which are normally distributed. Since there's some variation, some are going to be slightly bigger, some slightly smaller, and many things are normally distributed. On average, so we know that the mean is equal to, or we're told that the mean is 20 millimeters, which is handy because that's what we're looking for, and the standard deviation is equal to 0.1 millimeters. Now, we're going to do what the mean is and what the standard deviation is in the statistics part, which is what we're going to be doing next. So in that respect, this is doing things the wrong way. But so the question is, how many of these are going to be rejected? So I mean, that is that you can look up, that was the question. So from 10,000 parts, how many will be rejected? So when we look up our tables book, it tells us so when you look up the table book, they have a kind of normal distribution, and then they tell you what the probability is that your component is less than or equal to this much. So they have a standard normal distribution, and you just look up in the table book how far, what the probability is that your component is 1, 2, 3, 4, or 5, or I don't think it goes up to 5, but 1, 2, or 3 standard deviations away from the mean. So table book tells you the probability that normal distribution is less than or equal to Z standard deviations from the mean. So how do we do the question? Well, this is for the table is for the standard. This is the standard distribution. So that's for standard normal. So that means that the mean is equal to 1. And the standard deviation is 1 as well. So what we do is, first of all, we work out z. And for that we go, well, I'm interested in how many things are within 0.25 millimeters of 20. So we go z is 20.25, because if it's more than that, then it's rejected. So I want the probability that it's less than 20.25 millimeters. And z is, the how many standard deviations away you are from the mean. So I'm going to do 20.25 minus 20, because our mean is 20, and our manufacturer makes things which have the mean of 20 and a standard deviation of 0.1. So I divide that by 0.1, since I want to know, I'm thinking in units of standard deviations. So I'm looking, I want to see what's the probability that the things that I manufacture are 0.25 millimeters away from the mean, because that's my tolerance, and I divide that by 0.1 because I'm working in units of standard deviation. And if I do that, well, I'm looking for variations which are less than or which are greater than 2.5 standard deviations. And if you look that up in the table book, you just look up, z is equal to 2.5, you get 0.9938. So that's the probability that my manufactured component is less than or is less than or equal to 2.5 or 0.25 millimeters from the mean. So the probability that the manufacturer makes something which is acceptable is 99.38%. So probability that it is rejected is 1 minus that. So that's 0.0062. Now there's one extra, or one catch. So this is the main mistake that you're likely to make. So firstly, you need to work out how many standard deviations am I interested in. So there I just go, well, I'm interested in, like, my tolerance is 0.25 millimeters. So anything greater than that is rejected. But that's not in units of standard deviation. So I divide that by 0.1, and that's how I get the 2.5 standard deviations. So Z is 2.5. Then I look up 2.5 in the table book, and I get 0.0062. So the part that people slip up on is they forget that a component can be too big or too small. So I don't want my pieces to be bigger than 20.25, but I don't want them less than 19.75 as well. So that means I have to double the answer, since the normal distribution is symmetric. So you can have can be too big or too small, So double. $124. Because the question was, from 10,000 parts, how many will be returned? Well, if the probability is, okay, if the probability is 0.0062, then from 10,000, so from 10, that'll be 0.06. From 100, it'll be 0.6. From 1,000, it'll be 6. And from 10,000, it'll be 62. But since it can be too big or too small, you end up doubling it, so you get 124, which is the correct answer. Then there was one other part in the question which just checks to see how well you know the stuff. So we're looking at the same problem, but there's a slight change. So for some reason the machine got damaged, and it's actually now producing components which have a mean of 20.05 as opposed to 20. Now the standard deviation is still the same, so that's still 0.1. So now what happens? Well, again, we just need to work out Z. We're looking for, so if it's more than 20.25 millimeters in size, it's going to be rejected. So I want how many things are less than or equal to Z is 20.25 minus 20.05. So that's going to equal 2. Or so that's 19. It should be 19.75. So then that, so since now the average is too big, in order to get it too small, it'll be harder. You'll need variations which are 3 standard deviations from the mean. So in other words, you're unlikely to make things, you're far less likely to make pieces which are too small because your average is now 20.05. So you'll need to make something which is 3 standard deviations away in order to be too small. Likewise, now the mean is bigger, so you only need it something to be 2 standard deviations away now to be too big, while before you needed 2.5 standard deviations. So we just work that out, and we get, we just look it up in the table book, and we get 1 minus the probability that or Z is less than 2, so that it's acceptable. So that's the probability that it's acceptable. So 1 minus the probability Z less than 2 means it's unacceptable, and that works out at 1 minus 0.9772. When we do the same thing here, we have the probability 1 minus so the probability that Z is less than or equal to 3, if it is, means it's acceptable. 1 minus that means it's unacceptable. So that's going to be 1 minus 0.9987. So you can see the number that are going to be rejected from this for being too small is very small, while the probability that it's going to be too big is a lot bigger. So when we add this up, we get 2 minus 1.9759, which is 0.0241. So this kind of checks to see that we understand all the bits and pieces more, because it's easier in the other case, because all you had to do was double it. So that's all we needed to do extra for a higher level. As always, you want to kind of practice doing questions from your book, because it'll have a good collection. But once this is all you need to know, and this is literally, I mean, this is from a past paper, a quite recent past paper. So this is all you need to have known to do that.